in this video, we're going to talk about exponential and logistic modeling. So in the very first part, if a population P is changing at a constant rate R each year, then you're going to have your P at T is equal to P sub 0 times 1 plus R raised to the T, where P at 0 is, of course, your initial population. R is your rate, expressed in a decimal, keep that in mind. And your time is the T, as usual, in years, so make sure you keep that in mind. If R is greater than 0, then R plus 1, or 1 plus R, is the growth factor, and R less than 0, then R plus 1, or 1 plus R, is the decay factor for the population. Right, so tell whether the population model is an exponential growth or decay function, and find the constant percentage rate growth or decay. So for the first one, you've got P at T equals 102,324 times 1.025 raised to the T. So think about what is 1 plus R. That's going to be equal to 100%, because it's one whole thing, plus 0.25. Oops, missed a 0 there. 0.025. So your growth rate, if you move your decimal over to make that a percentage, is going to be 2.5% growth. Right, so let's look at this one right here. Well, your 1 plus R for here is 0.92. So to rewrite that, that looks like you really got your 100% minus your 8%. Because that really, you could change that to 92%. And so this looks like you've got an 8% decay. And again, notice how it was your 100% always. And then if you had more than 100% or less than 100%, that was your growth factor or your decay factor in these. All right, so for our next one, we need to determine the exponential function with the initial value, P sub 0 is 12, increasing at a rate of 6% per year. So again, start off with your formula. Remember, it was P sub 0 times 1 plus R raised to the T value. And so it gave you that P sub 0. So I'm going to do P sub T equals, your initial was 12. They gave you that, times, and they gave you 1 plus, and it said 6% per year. So 6% per year. And so we're not going to leave it like that. Remember, 6% is the same thing as 0.06 as a decimal. Remember, that was always a decimal. So your final answer would be 12 times 1 plus 0.06, so 1.06 times t. Okay, so moving on, we're going to talk about bacteria. Oh, yay. So looking at the bacteria part, we've got to solve algebraically. They're giving us 100 bacteria. It's put into a petri dish, and the culture doubles every hour. Oh my goodness. Predict when the number of bacteria will be 250,000. So again, here's our formula. Here's what we're starting with. And to fill this in, we have P at T equals 100. Excuse me, that's our starting. So we have 100 times, and it said that we're going to double every hour. So our rate is doubling every hour. So it's already solved our growth rate for us. It's telling us right here it's doubling every hour. So this portion inside here is going to be a 2, because that 1 plus r, that was our growth rate or our decay, and it's already told us that it's 2. So this is going to be 2 raised to the t power. And this wants to know or predict when the number of bacteria, so the time, notice it said when, so that's talking about our time t. The number of bacteria will be 250,000. So we're going to put 250,000, and yes, you can use a calculator, equals 100 times 2 raised to the t power. So you would divide both sides starting out by 100. And so those would cancel. Those would cancel. So looks like you've got 2,500 equals 2 raised to the t power. And to solve that, what you need to do is take the natural log of both sides, or you can sit there and go through your powers of 2, which aren't going to turn out so great for you. This is something new that you've not seen yet, and that's going to be, you're going to say ln, natural log, of 2,500 equals natural log of 2 raised to the t. And the reason why you do this is because of this next step. You're going to be able to move this exponent down to the front. So you have t times natural log of 2. Now you've got your variable down to the front. So you can divide both sides by natural log of 2. So put this in your calculators. And so your time t should be at 11.287 hours. And don't worry about solving it graphically. We'll just look at it on the algebra side. So again, we set this up. And I think y'all follow along pretty good until we hit about here, because this is new. And again, the reason why we had to do natural log is because we had our variable in the exponent. And anytime you have that happen, you have to move that t down to the front. And to do that, you have to do natural log. Okay, for our next one, we have a half-life. And so we're talking about of a certain radioactive substance is 40 days, and there are 8 grams present initially. Find the time where there will be 1 gram of the substance remaining. So again, our formula P at T is P at 0 times 1 plus R raised to the T power And so let's go ahead and list out our initial, they told us was 8. Our base part, this part right here, is 1 plus R. But then they told us right here it's a half-life. So this is decay. And it's going to be a 1 minus a half, which is going to generate a half. So, and we want to know of a certain radioactive substance is 40 days. All right, so when we write out our P at T, remember P at 0 was 8, and then times, and we figured out 1 plus R is actually a half. And normally we would raise it to the T, but since we're dealing with a half-life, it's going to be our time over 40. And again, that's because you're dealing with your half-life. So again, do keep that in mind. If you're dealing with those half-lives, this is how your time will look. Your time over 40. All right. Now, to solve this, I'm thinking it might be good for you to do a calculator problem on this. On your calculators or Desmos, either one, put in y1. You're going to solve this. You've got 2 functions, and you're going to find their intersection. Do your first function is going to be 8 times 0.5 raised to the x over 40, and make sure that x over 40, all that's in your exponent. And then you're going to do y2, and that y2 is going to be your 1 gram, because you want to know when they hit each other. So that's going to be 1. Now, algebraically, you could set this equal, you really could solve it over here. Set that equal to 1 equals 8 times 1/2 to t over 40. And then divide by 8, so that's 1/8 equals 1/2 raised to the t over 40. And then do your natural logarithm. So you've got natural log of 1/8 equals t over 40 natural log of 1/2. And then divide by natural log of 1/2, and then multiply by 40. So we've got natural log of 1/8 divided by natural log of 0.5. I'll take care of that, and then let's multiply by 40 to get it out of the denominator. That equals t. So there's a bunch of algebra, or you could graph those two and find point of intersection. Either one is correct, and both of them should come up with 120 days. All right, uninhibited growth of cells. All right, so for this, you're going to grow without bounds. So we're going to have E in this. So A sub t equals A sub 0 times E raised to the kt. Both of those k and t are in the exponent. And of course, k, since it's a growth, k has to be greater than 0. And this is the growth rate of the cells. All right, so now we're back to bacteria. And we have a culture of bacteria that follows the law of uninhibited growth. If 500 bacteria are present initially, and there are 800 after 1 hour, how many are present after 5 hours? So we have two different things that we can look at here. So first of all, we need an initial value, which we saw right here. So I know at 0, there was 500 bacteria. And let's see, after 1 hour, there are 800, so I know this. And so, can we set up a formula? So, our formula that we could possibly set up, we have A at t, and we need an initial value, which is going to be 500. And then we have E raised to the kt. And let's see, we know after 1 hour there's 800, so really we could solve for some of this. So we could solve for k. So if we solved for k, we could say 800, because I know that value when time is 1. So 800 equals 500 E raised to the k times 1. So we can divide over 500. 500 under 800, that's really going to be 8 over 5, isn't it? Once those zeros cancel. Equals E to the k. We'll have to natural log it again because our exponent is our variable. 8/5 equals natural log of E to the k. So natural log of 8/5 over natural log of E equals k. Now natural log of E, something to put over here, natural log of E is always 1. So natural log of 8/5 is k. Now, natural log of 8/5, put that in your calculator, and you get k is approximately 0.4700. So now we have a value for k. So now we can go back and finish out this formula right here. So A sub t equals 500 E raised to the point, I'm just going to say 0.47 t. Now we can answer the question, how many bacteria are present in the culture after 5 hours? Now we just plug in 5. We couldn't at the beginning because we didn't have a completed formula to plug into. We had to, our completed function. So now we go plug in. Comes E to the 0.47. Well, that looks like a T. times 5. And you should get, when you plug all of that in, 5 is going to be 5,242 bacteria. Okay. So looking at part B, how long before the culture contains 20,000 bacteria? Well, we are going to use this portion right here. That was our completed formula with the information that we have. So how long is it going to take? Well, we're going to say 20,000 is equal to 500 e to the 0.47 t. Okay, and so dividing that 500 over, that's going to leave you 40 equals e to the 0.47 t. We're going to do the natural log of both sides. So we have natural log of 40 equals natural log of e, and then I'm going to bring down that exponent. So I'm just going to say that times 0.47t. Because you know the exponent's going to move down once I do the natural log. And natural log of e, again, we said that was going to be 1. So that goes out to 1. And then we're going to divide both sides by 0.47. Okay, and so when you put that in your calculators, t is going to be about 7.848 hours. And I think we needed this though in minute, I don't know. So if we need minutes, the ratio there for the minutes, I don't know if we needed. It's about this portion here. If you convert that over to minutes, it's 7 hours and 51 minutes. If you need it. All right. Okay, so using regressions to model decay, and they want you in part A, they tell you all the stuff in the example, and then using a utility to fit the exponential function to the data. Our calculators can do that, but I'm not going to take time to go through and show that. I'm going to go ahead and just give you what the equation is. It's going to be 100.367 times 0.879 raised to the x. All right, that's the equation you would have gotten. Now for part B, what is the half-life of the radioactive material? Well, they start us out with the very first thing, the initial at 100. So we're going to take this and we're going to say the half-life is 50, and we're going to set that equal to what we found as the whole thing. And we're going to solve this just like we did the others. We're going to divide both sides by 100.367, and that's going to give us 0.49817. I'm going to assume y'all do this on your calculators. Equals 0.879 raised to the x, and then you're going to take the natural log of both sides, and so you're going to end up with the natural log of 0.49817 divided by log of 0.879, and that's all equal to x. All right, and then again, putting that in your calculator, x is going to be approximately 5.4 weeks is your half-life. All right, part C, when will there be 10 grams of the material left? So we are going to set 10 equal to our original, so that's 100.367 times 0.879 raised to the x. And we solve for x again. And so here we are going to say that we divide over by that 100. And keep in mind, once you divide over by the 100, that's going to give you, I didn't do this one, 0.099. We'll throw a 6 there. Equals 0.879 raised to the x, natural log of both sides, right, and now we will move our x down to the front, and so when we do that, now we're ready to divide both sides by our natural log, 0.879, natural log of 0.879. And when you put that in your calculators, you should get, make sure the right answer, 17.88 weeks. That's what I got. All right. And then part D, how much radioactive material will be left after 52 weeks? So that one we're going to plug in for time. So y equals 100.367 times 0.879, and this time we're going to raise it to the 52nd. So in your calculators, type all that in, and you should get approximately 0.123 grams. All right, so a lot of plugging in there. All right, so we're going to talk about Surfside now. High school has 1,500 students, and these students start a rumor. No, not a rumor. Which spreads logistically so that you have all of that. And it models how many students who have heard the rumor by the end of the day. And t equals 0 is the day the rumor begins. So, part A, how many students have heard the rumor by the end of the day? 0. So we're going to say S at 0 equals 1,500 over 1 plus 38 e to the 0. And if you type that in your calculators, you get S at 0 to be approximately 38 students. And part B, how long does it take for 1,000 students to hear the rumor? So for 1,000 students, This one, it would be a great day, goodness, a good one to graph and find intersection of the two. So the first one, you would do the first graph, you would type in, is going to be the graph that they gave us, 1500. And this one might be done easier on Desmos because of the big numbers. 38 e to the negative 0.9t. There's the first one. And then the second one you're going to graph is 1000. And so you graph and find intersection. And find their intersection. And it looks like possibly, looks like you might get about day 5.